Dear students, welcome back to the second semester BSc Physics class. In this session, we shall discuss about Clausius Clapeyron first latent heat equation, its importance and derivation. Before proceeding, I am sharing an interesting video which I found on YouTube. Please watch it. It is related to our today's discussion.
Have you ever wondered why ice turns into puddles of water on a sweltering day? Keep watching and you'll find out. On Earth, materials exist in one of three main states of matter: solid, liquid, or gas. Materials can change between these states. When a state change occurs, a substance's property will also change. Maybe not too surprising. However, if the state change is reversed, the substance will recover the properties it had to begin with. Neat. Matter can transition between the three states when heated or cooled. But why is heat key in all of this? When a material is heated, it absorbs heat energy. This additional energy can cause attractive forces between molecules to break. This leads to rearrangement of the particles because the attractive forces no longer hold them together as tightly. The same happens when a liquid is heated. The attractive forces between the molecules break, leading them to become more widely dispersed and a gas to form. These four words describe changes in state. Do you know which word refers to which change? Pause the video, fill in the gaps, and click play when you're ready. Did you get them right? Do you know the difference between evaporation and boiling? Both are when a substance transforms from a liquid to a gas. Think of a boiling pan of water, all of the water bubbles. This is because all of the particles have enough energy to become gaseous. But water standing in a pan that is not being heated by anything other than the environment can also turn into a gas. This is evaporation. Only the particles at the surface have enough energy to change from a liquid to a gas. Hence, evaporation is a slower process than boiling, even though it achieves the same state change. Both are types of vaporization. The opposite of these vaporization processes is condensation, the transition from a gas to a liquid. Think of a cold can of soda on a hot day. Those water droplets on the outsides, or the dew on the grass in the morning, or the steamed up mirror after a hot bath, even the clouds in the sky, or a foggy windscreen in a car. These are all examples of condensation. Water vapor in the air has cooled down to form liquid droplets of water. Now let's think about the transitions between solids and liquids, so melting and freezing. Think of the Arctic Sea ice. In the summer, when air temperatures are warmer, more heat energy is absorbed by the ice. This causes bonds to break between the ice's water molecules, and the ice starts to melt. The solid ice becomes liquid water. But in the winter, the air temperatures are colder, and so seawater freezes, and the ice starts to form again. There is less heat energy within the ice, and so more bonds can form, holding it together as solid ice. So far, so good. But did you know that sometimes when solids are heated, they can turn straight into gases? This is called sublimation. This is only demonstrated by particular materials such as solid carbon dioxide, also known as dry ice. When subjected to a certain pressure, it will turn straight into gaseous carbon dioxide. Liquid carbon dioxide does exist, but it only occurs under very high pressures. Similarly, gases can turn straight into solids when cooled. This is called deposition. Let's check out how much you remember about the changes of state. Pause the video and fill in the blanks. Did you remember them all? Our final thing to discover is that when a material changes states, the mass stays the same. The density changes, so the mass per unit volume, but the mass does not change. Our glass of nice cold Coke weighs the same whether the ice is solid or when the ice has melted. So there we have the changes of state. Just remember that the mass stays the same whatever the state.
From the video, we got the information about change of state of matter in different ways. Here you can observe a solid. Here we have taken the example of ice. A solid in the form of ice, it changes its state on melting and it converts into liquid, that is water. On absorbing heat, the water again changes into water vapor. So here the transition of these states from a solid to a liquid is known as melting, and from liquid to gaseous state it is known as evaporation. If this process is reversed by releasing the amount of heat and by decreasing the temperature, the water vapor or the gas on condensation becomes liquid or water in this case, and again by cooling this liquid turns into a solid. This process is called freezing. Here in general, if you plot a graph of pressure versus temperature for the transition of matter, we will get different phases. A solid changes into a liquid and the phase change is done by melting, or in reverse it is known as freezing. If a solid directly changes into a gas without going to the liquid phase, it is known as sublimation, and the reverse process of gas converting into a solid directly is known as the deposition. A liquid changes into a gas. The phase change is given by vaporization, and the reverse process is known as condensation. So here between any two phases we will find some equilibrium state where the two states are present. Whenever there is a change of state, either from a solid state to a liquid state or from a liquid state to vapor state, temperature remains constant as far as change takes place. This temperature, either it is a melting point or the boiling point, this temperature depends upon the pressure, and it is a characteristic of each substance. That means the melting point or boiling point depends upon the pressure. We can use an example here. You know, in general we say what is the boiling point of water? It is 100 degree Celsius. But the boiling point of water is 100 degrees Celsius at sea level. But the same water boils at 72 degrees Celsius on the peak of the Mount Everest. The reason behind this is the pressure. Therefore, pressure is a factor which affects the boiling point and the melting point as well. The Clausius Clapeyron equation is very important in understanding the relation between pressure and the boiling point or melting point. It was a very beautiful equation which was initially proposed by a German physicist, Rudolf Clausius, in 1834, and then further developed by French physicist Benoit Clapeyron in 1850. The Clausius Clapeyron relation characterizes the transition between two phases of matter. The Clausius Clapeyron equation shows that how melting point and boiling point vary with pressure and was derived by Clapeyron by applying second law of thermodynamics. Later, Clausius obtained the same relation by using Maxwell's thermodynamic relations. Here you can see the picture of Rudolf Clausius and Benoit Paul Emile Clapeyron. Now let us move into the derivation of the Clausius Clapeyron first latent heat equation. From the second law of thermodynamic relations, that is the Maxwell's second thermodynamic relation. The Maxwell's thermodynamic relations help us to express the state variables such as pressure, volume, temperature, etc. in terms of measurable physical quantities. These Maxwell's thermodynamic relations will be learned separately in another session. Here we can just use the Maxwell's second thermodynamic relation as it is. Here you have an expression dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. So here dou S represent the change in entropy to the change in volume at constant temperature, that is equal to the change in pressure to the change in temperature at constant volume. Multiplying both sides by T, we have T into dou S by dou V is equal to T into dou P by dou T. But we have the relation TdS is equal to dQ. Therefore, we can rewrite the above expression as dou Q by dou V at constant temperature, that is equal to T into dou P by dou T at constant volume. Here the quantity dou Q by dou V at constant temperature represents the amount of heat absorbed or rejected per unit change in volume at constant temperature. As there is a change in volume due to the heat absorbed at constant temperature, the heat represents the latent heat used when a substance changes from solid to liquid, which is known as a melting, or liquid to vapor, which is called as boiling state, when the temperature remains constant during the change of state. So here in any change of state, the temperature remains constant during that process of conversion of one state into another state completely. Here the latent heat L is known as, it is defined as the heat energy that is absorbed or released during the phase transition of a substance. If the latent heat L is the quantity of heat required to change the state of a unit mass of the substance, and V2 and V1 are the corresponding specific volumes. Here V1 is the initial volume and V2 is the final volume of the substance when it changes the state from one state to another state, that is during the phase transition. Now we can write dQ the amount of heat required, or it is the amount of heat absorbed or released for the change of state, that is equal to L, which is the latent heat, and dou V, which is the change in volume, that is the difference of the final volume minus the initial volume. Hence, we can write dou Q by dou V at constant temperature is equal to L divided by V2 minus V1. This means the change in heat to the change in volume at constant temperature can be written as the ratio of the latent heat to the change in volume. That in turn gives us L divided by V2 minus V1 is equal to T into dou P by dou T at constant volume. This gives very important relation dP by dt, that is equal to L divided by T into V2 minus V1. This is, we call it as the Clausius Clapeyron first latent heat equation. Here the dt is the change in melting point or boiling point due to the change in pressure dP. This is known as the Clausius Clapeyron latent heat equation which we require. This Clausius Clapeyron latent heat equation can be applied to the change of state from liquid to vapor or from solid to liquid. So this is a very beautiful equation we got from the Clausius and Clapeyron in order to understand different things involved in the change of state of a substance or the transition of the state of a substance. In the next session, we shall discuss about the effect of change in pressure on melting point or boiling point of a substance.